Welcome back. It's the final part of our Intel Xeon Phi training series here for Nick. My name is Vince Petro, and I will be giving you all a little bit of background on some real-world examples that we've done, although I've spoken to some of those in the first presentation. I'm going to try to get into a little more depth here, and I'm going to go through a really excellent optimization example that I got courtesy of Jim Jeffers and James Rogers, who wrote a book on programming for the Xeon Phi. So this is a direct rip-off of their example, which I very much appreciate. And without further ado, we'll get started. I'll also point out, actually, there was one further ado. I'd like to thank Mr. Shane Sawyer for his contributions to this presentation, specifically in the VTune section. We may or may not actually get to that, but if you don't, please go download this and watch those two videos of how to use VTune on Beacon in order to optimize your code. All right, now we'll get started. So once again, thank you to the National Science Foundation for giving us a grant, which has made this possible. Anything I say here is not necessarily representative of anyone else. The real-world examples, a little bit tune profiling, and memory alignment and vectorization. I may switch those because the memory alignment and vectorization is hands-on, and I want to make sure we get the thing you would watch. One of the things I want to point out again as a reminder here, when I'm doing these comparisons, I'm comparing one Xeon Phi to two bridges. That is, as you see, it's approximately the same power consumption at that point. We're looking at approximately the same amount of vector space, although spread out a little bit more. And I'm always running the same code on both. What we'll find is when you optimize the code for the Phi, it will in turn run much faster on the Xeon. So comparing the previous unoptimized version of the code on the Xeon to that which is optimized on the Phi is unfair. That's it's like comparing it to a Lamborghini without an engine. Again, the point of this is to give a comparison, even though it doesn't seem very fair right off the bat, because the Xeon has we've now kind of given them equivalent abilities, but the Xeon has 2 points the clock speed, right? Something serial is going to get blown away by the Xeon. But we can use the threading and the versatility of programming and the memory alignment very well. We can use the Xeon to blow anything we could do in a traditional CPU. A quick reminder, here are some of the different codes that we at ACE have ported over, and some of which we have optimized, everything from atmospheric modeling to magnetic physics to ACE modeling. All right. Dr. Robert Harkness passed away a little over a year ago. He was the main developer on the Enzo code, who's since moved on to other folks. This is some of his work. The interesting thing to posit here is twofold. One, this is a code that used third-party libraries, Hyper and HDFI, both of which were recompiled for the Mike fairly easily. Using configure script. The point of this presentation, or part of the presentation, is to show you that, again, this is looking at scaling not so much versus a Phi versus a Xeon, as just that as you set threads on the Xeon Phi, up to a certain point, right, to get faster and faster and faster, nearly linear, okay? In a particular case, after 2 threads, you see it start falling off a little bit, and that's because there's not enough work to be done per thread. This is a great example. If you have a 128 cube mech, which is reasonably large, but it's not ginormous, you're going to see that you don't get a whole lot of benefit as you add threads. You get a little bit of benefit, but not a ton, because this doesn't have enough to do. And when you have these larger and larger and larger meshes, you notice that curve becomes steeper and steeper and steeper. And once again, we're talking about a function of having enough work, all the threads, to stay busy the whole time and justify the context switch, which is faster on a Xeon Phi than on a Xeon, but it still requires context. All right, is the magnetohydrodynamics code, or the magnetospheric physics code. One of the things that really is interesting about this is that it's MPI-only code and uses dynamic load balancing, and yet we were still able to scale it to a very high number of cores. And this 64 MPI processes, 61 MPI processes on a given KNC card. Again, you'll notice this graph's a little funky looking. That's next to Excel, and it's rounding. This line sheet, the little dotted line, should be ever so slightly above this. That gets pretty doggone close to ideal speed up, and that's really excellent. That's a good sign for those people using MPI that want to scale over a card. Now, they only have 8 gigs to feed those 61 cores of MPI. So you've got to have a specific kind of problem and a specific kind of decomposition to take good advantage of it, but you can't. All right, at least example as last time, but this one I want to go into a little more depth on. We're talking about a Boltzmann equation, BGK collision approximation, the CFD solver, where we're looking at gases, specifically highly rarefied gases. And things are operated a little differently than they do under a traditional Navier-Stokes Reynolds average model. You need to look at things as a collision set, because you have a whole lot less moving through. So, well, some of the things we looked at, and we're going to be looking at these same things in a moment here, we'll do some examples. Okay, anytime you vectorize a loop, we can unroll a loop, we're going to do better. You know, that's no news, right? Better to vector than a scalar. All right, data sets. We did make sure to align our data with the buffers, the caches, all those things on the line. Parallel sections. Okay? Every time you spawn threads and then collapse threads and then spawn threads and then collapse threads, or fork and join, if you like that part of the line, you sign. And when I mean serious important capital, that is what's going to make a file worth your while. All right, dependencies. All right, so again, anytime that you have a loop that's got something weird that you really like to get rid of so that you can unroll it, if you can pull that outside the loop, that's one. All right. This is an example of instead of having a critical section, using a reduction. All right, with a variable. I'm going to save you some trouble. Right? And these last two of the last three are precision. You can use single precision versus double precision. You got twice as many calculations as you can do vector calculation. Go beyond single precision and integer precision, there's 2 times more again, and again, and again, and again, and again. Okay, so, you know, you can really take advantage of things if you just lower the precision a little bit. And there are certain calculations that outcome doesn't have to be to 16 digits of precision, decimal after 10 to the negative 15. But precision, so don't use it. Don't waste your memory. Don't waste your vector. All right, and compiler hints. All right, and this is actually should be called hitting the compiler over the head now. Saying instead of hinting, maybe you want to vectorize this loop. As nudge, we're saying this loop has no dependencies. If it does, I don't care about them. I just want you to vectorize. Period. That's what Prezi does. Based on all these optimizations, each time optimization, the code got a little better. The bigs were, and this is not a shocker, vector, right? And precision. Now, those actually feed into vectorization, right? One is utilizing the vector units on the Phi, which is one of the big advantages. The other one is utilizing them even better by lowering precision and being able to do twice as many calculations in that same vector operation. So those are 2 things that give the most yield. Now, the other thing you'll notice that's interesting here is the balance and scatter of reticles. Okay, so there's normally, you used to probably the concept of compact, where it's going to put, like you have 60 cores, right? You get for 120 threads. You compact, it's the first 30 cores and put all, 4 threads, 30 times. Smush them all together as best as it can. And that's generally not going to do you a lot of good because you're going to end up with contention over memory, over arithmetic units, all sorts of things. Then you have diametric opposite, which is scatter, which have 120 threads that I ask you to put 2 on each one of them. Okay? And then there's magic. We don't really know exactly what it does because it's based on heuristics that Intel changes constantly based on their, operating system and their new software stack. Balance is often more than not at scatter. Occasionally, what it will do is it'll be cognizant of where OS processes might be wanting to hang out and look at some other things that's determining what you want. You'll notice, by and large, balance does as well or slightly better than scatter. Although there are occasions, a couple right here, one right here, where it doesn't do quite as well. And that's not really something that's over here, okay? And probably a function of the fact that, sure, right here, as we've got precision, the tension on those arithmetic units is dropped. And so scattering is not quite as useful. When we did this, again, you can see here that on a Xeon, the speed up, you get up to 16, right? Hyperthread up to 62, and at that point, you have no more speed up. It will not faster than that. You actually hyperthread, or you see it has nice linear speed up. In this particular case, nice linear speed up to about 61, and then it's peter off as you hyperthread all to 4 threads per core times 61, which is 44 threads. Okay, I know it says 256, but that's just because of the gradation. This is not looking at that. This is saying, look, I can keep scaling. This, relative scaling on that last plot says, I think I actually might be able to beat it. But really, if you're comparing the phi with the phi and the Xeon with the Xeon. Here we want to compare Xeon versus phi. And when we see that we can knock off some time. I know it's hard to see on this particular plot, but one can knock off some time, even if it's just, tenths of a second. Okay, and we're talking here about the log wall time, and that being like 3. So we're not talking about long wall time. So that percentage is reasonably significant, 2-4% you can knock off by using the phi to its fullest extent versus using the Xeon. So this next part, this presentation, was used by me and Jim and Jane on several occasions to do training. So I'd like to thank them for putting this together. I'd say putting their book together. And this is something that came out of chapter 2 of their book. Again, the book is called Intel Xeon Phi Coprocessor High Performance Programming. The book reads a bit like a novel, surprisingly, and lots of great examples. Optimization tips for both the Xeon and the Phi. Because anything you do to make the Phi better generally makes the Xeon better. We're going to do a little high-speed test drive, all right, called Hello Flops. Now, see flops meter at 2.114 teraflops per second. Okay, that is the peak Intel Xeon Phi card using single precision. No precision, it's about 1 teraflop, half. Okay. Real quickly, these are the cards we're working on here, right? Clock frequency just over gigahertz, 60 cores, 8 gigabytes of RAM, 5 gig of transfer memory. Again, you're looking at the peak double and single precision flops, okay, and peak memory bandwidth. Here's the code we use, and I'm going to, we're going to back out of here in just a second. This is the code. It's fairly simple, straightforward code. The point of the code here is really not to do anything complicated. The code here is actually just to do a simple fuse, multiply, add, where you've got a scalar multiplied by a vector added to another vector. Show how the card's prowess at doing fuse, multiply, add, and vector form. Okay, now, what you'll see here is a lot of other junk, and a lot of other stuff is literally just set up for timing, for flop counting, and so on and so forth. Okay, and all that's actually occurring here is we're creating two arrays, adding them together, and multiplying the first one by a coefficient, and getting the result. Now you'll notice that this is not set up in a special way. Okay, there's no pragma SIMD or pragma IV depth. This code is, as far as we're concerned, we have no concept when we wrote this code. Vector process, everything is scalarly. So, what performance do we expect out of this, right? This is, it was vectorized. We don't know it's not, okay? If it's vectorized with single precision floating point, we should do 16 operands per cycle, okay? Fuse multiply, so you can double that, so 32 operations per clock tick. Clock tick is 1.05 gigahertz. That's how many, you have 1.05 billion clock ticks in a second. That's what a hertz is, okay? And then, of course, how many cores and how many threads, right? Every time you add another thread or another core, actually speaking, you should get some benefit out of that, right? So the P formula is 16 times 2 times the number of cores, all right? As far as that would be 32 times how many cycles, right? So 32 billion, 2 gigaflops, all right, per core. That's what we're expecting. Okay. At 30. Okay, so we did 1.05, so 33.6. Forgive me on that math. So that's pretty reasonable, right? We should still do 33 gigaflops with one core, one thread. So let's get the world, see how it works. All right. So SSH into beacon. Well, that was not my full word. My Lustre directory. All right, and chapter 1. So I'm just going to make everything that it can. Okay. Now here, I said ICC minus OpenMP, runs OpenMP program, minus 3, so optimize as much as you can. Minus report equals 3. So what that says is try to vectorize the compiler. I'm not saying how or when or where, but try, right? And that's what we're assuming. We're assuming that we didn't know anything about vectors, but the compiler magically vectorized it. How cool is that? Let's see how that works. Okay, here that it says that we have 2 different loops that were vectorized and one that was not. All right, we are calling this to be running the mic, and let's do so. So what I'm going to do is I'm going to do a do that. Do a mic SCP to this file, right? Hello, block. Block 1.4.5 to temp.dir on my. Because I haven't. Submitting for a computer. I'll actually have a temp.dir to work with. Yeah. There it is. Source code, you see there is no, I'm not telling it to vectorize. It's all about the compiler. I don't know anything about vectors. It's a serial scheme. Yeah. Okay, well, right. That, well, of course, this one we're only doing with one, you know what it is? Not for all of them. This one we're only doing with one thread. So, good catch. All right, so then an OpenMP code, again, obviously clueless about threading, vectors, all of it. What we've got going for us is the compiler with the, hey man, I can wait for that. You told her. Let's see what performance we get. So I am going to, I'm here on the card, I am going, or compute node, do Lustre directory, and P again, and now I'm going to do Mike SSH to get to the card. All right, cd to tempter, and I should see my executable. I'm just going to run it. See what happens. So we got 25.6 gigaflops. They're hoping for better, right? That's okay. It's pretty close. We were saying 33. We got 25. In the scheme of things, that's not even, it's the same order of magnitude. Okay. Now, might it be lower? Well, right now, one of the things that we did that was crazy talk was printing to the screen. Okay. That makes the mic actually have to go talk to the Xeon, and then the Xeon prints to the screen. All right. So we have done some things in this code that are external to just that simple loop structure that we're going over. Variable initialization, I/O, those things are going to cut out from some of your performance. Okay, so now that we've done that, back to the presentation. And next slide. How about using OpenMP? So now we're still smart enough to necessarily know much about vectors, are smart enough to know about OpenMP. Now here we're just using two threads, and we're setting compact. That means it's going to stick both of those threads on core number 1 of the Xeon. That's okay, because we share an ALU. Okay, no big deal. And you notice you've got Pragma OMP parallel, we've got a master initializing thing, we've got a parallel for loop, Pragma OMP parallel for, we're going to go through and it's going to send this off to two different threads. All right, so same code, same things, just a little different. Now, you'll notice this offset. The purpose of the offset is you just have a singular array. Okay, and in order to easily divide it up, or actually I should say easily, in order to for a certain division, we set this offset so that thread array 1 and thread 2 gets array chunk 2, and that's just how it works. We don't ask to split it, we don't ask it to put the arrays in two different places, we just have a chunk and a chunk, and there's no duplicate. Hello, flops 2. And we're going to see what we get. I'll hop off the mic here, and I'm going to do make hflops 2. All right, and here, again, it says loop is vectorized, heel loop is vectorized, remainder loop is vectorized, loop is vectorized, and, you know, there were two loops that were not vectorized. No biggie. Okay, two specific loops were not inner loops. It's going to provide the inner loop, not the outer loop. We've done that compilation. We do a mycp over to tempter of hello flops 2. Our mic SSH over to that mic. I'll point something out. As I'm sticking things on the mic, using up its memory. Actually, I'm not. These are on temp, excuse me. If I was putting them on the user or on /temp on the mic, I'm using up RAM, and that's probably a bad idea. So what I'm doing is putting them on the SSD on the node, which affects the mic memory. So let's go to the temp ver, and let's run hello flops 2 and see what we get. We'll look at double our performance. Any idea why? We had threads. We had contexts that were able to do that very same thing. And they each their own arithmetic unit to work with, so there was no sharing required. So you see where we're going here. We're slowly but surely getting smarter and smarter about optimizing the code. All right, PowerPoint here for a moment. I'll probably be bouncing right back. All right, so here's the problem with this. This is not easy to test on because we have to go in and change what OMP set threads is and KMP set defaults is in the code and recompile it every time. That's how, thank God, OpenMP environment variables. Let's try it. Okay? So we're going to make this, we're going to set affinities, set some different thread counts. We're going to look and see what we get. Okay? Here we go. So back over, hop back to CPU, make HFlops 3. Again, get smart enough to go, oh, vectorize that loop. Okay, cool. All right, I'll do it. Vectorize the loop. So, I should actually do this. This is kind of silly on my part. Let's take a look. This is going to hello flops 2, except you'll notice here we have OMP get num_thread, which it's going to grab from the environment variable, and then utilize the affinity that we tell it to utilize in the environment variable. Okay? So it's not set statically in each program, but otherwise everything is exactly the same. Okay, so we've compiled that. We're going to copy it on over to the mic. Then we're around and see what we get. All right, temper. These are codes. So we're going to do just any prompt call, not either of those. And we're going to see what we get. Okay. Notice here you've done 240 threads. Where did that come from? That's the car saying that's the most threads I've got. You didn't said anything, but you did say you wanted the thread. I'm at 40. That we're up to about 6. There's lots. Okay. That's shift on peak performance. It's pretty good. Now, that's wild considering that you have to share those arithmetic units between, 240. That means you use every core, every core, and 2 of those threads, or each set of 2, I should say, that's an arithmetic unit, which means it's going to slow down a little bit. It's going to have terms. Fortunately, these calculations are simple enough, and the operating system is smart enough to settle things in a reasonably intelligent fashion. So you'll notice that you were able to get almost that 2 teraflop performance. Okay? Just and using use thread vectorization, you should get that. Let's change some things up. So I'm going to do export OMP num threads 120 X can be affinity equals path. running through what we get. About a teraflop, okay? Let's see how it makes things any better. Well, we'll try it. Okay. So I'm just from compact to scatter. Code still on 120 threads, but now it said don't do them compact, scatter them out. Now that I get performance out of that. Wonder why? Well, I did scatter, right? In 120 threads. That means just for core, nobody share an arithmetic unit. What that means, 240 thread case, is that we could have really, if we had 4 arithmetic units on each card instead of just 2, we probably could have gotten 4 teraflops instead of just 2. Because we got almost 2 teraflops just using 120 and not making anybody share ALUs. Let's do this. Let's try balance. See what happens. I'm going to change this CMP affinity to the magic one called balance. Let's see. Yeah. Slightly. That could just be the slight lag in the team. It's actually getting a little worse each time. Okay. Probably because the machine is starting to try to clean things up from the last job, I guess. The balance is not automatically the cure-all. Situations work better with balance, some work better with scatter, some work better with compact. And it just depends on the type and frequency of your calculations. You'll want to try them all. Okay? Moreover, don't be afraid to oversubscribe threads. That's fine. Then you'll see hyperthreading give you some benefit. It's only 100, an extra 130 gigaflops. That's better than the performance we got out of this code with no vectorization at all. It's a significant margin. Okay. I'm going to do one other thing here. Let's just change things to 180. All right. So this is where everybody's got a share, but it's not forced bearing down on 2 exits. It's things, which we would be a little bit better. Let's see what happens. All right, here it made very little difference. Right? The threads are able to take turns in a reasonably effective way, so you lose a whole lot of performance. But you also gain anywhere near what you would have hoped to gain. You use by 50% more threads and gained effectively 0. And that's a function of the fact that this is a very arithmetic-sensitive code. There's not a whole lot of other stuff going on. Yes. Oh, way over. I did, technically. I can way oversubscribe, though. Like, technically, anything over 120 is over. Yet solid this, they're threaded context because they're sharing arithmetic. Yeah, it's 4 per core, and there's only 2 arithmetic per core. But we oversubscribe it just for giggles. Just see what happens there. Holy gorge. Yeah. No, that's not too bad, actually. I was surprised. It took longer, though, as you can see. I guess because of the factor of maybe 6 threads competing. Maybe the operating system is able to schedule those back and forth a little easier. I don't know. That's kind of a tough one. And oversubscription is always like that. Hyperthreading is always like that. Sometimes it works out great. You get benefit from it because things can turn in a real fashion. Other times, everybody's in a rush for the same thing all at the same time, and everybody leaves. So that principle of vectorization, threading, and optimization for on 5. That's the basic. That's really 90% of what you want to do, you can do right there. And you don't have to do anything like intrinsics, alignments, and all those other sorts of things to get this. Those things help and can make things even better. You're going to get even closer to that 2 teraflops perfectly if you remember, memory, requisite to get performance. And that's nice. You're not in offload mode, you're not having to amortize anything. You're just trying to straight performance out of the car. Is a teraflop, is a teraflop. Okay. We are about out of time here. So before I exit the compute node, let me just real briefly. So we kind of played around and we've seen that we can get about 2 teraflops out of it. Okay. There are other codes. There's a Fortran code to look at. There's another offload code. And you'll hear that if you were to run this offload code, it's actually to stay on the host compute node, right? And so that is that this particular offload code here, it is able to see there's no benefit to going off node. All right, new tutorials. I know they look crazy long, but they're only a couple minutes each. And where a colleague of ours, Shane Solaire, has put together some really, really excellent tutorials on using vTune. Okay, I am conscious right now. It's not. So I'm seeing it move through, which is kind of a bummer. But anyway, these are really good tutorials. They're not boring. They're only a few minutes, and he will walk you through running a hotspot collection in vTune, which shows you where areas of your code are that there's a lot of contention that might benefit from threading or vectorization. And then he shows correcting the code, running it back through with that OpenMP loop, and well, boom, much better performance. We run things in batch mode. It's a GUI. It's a very slow GUI. You're having to run that GUI, through X. And of course, you can't run it on your home computer without having Intel vTune Cluster Studio, yada, and that's non-trivial, non-cheap light. So we generally tend to run the thing in batch mode, and then when it's done, we will tunnel X, pull up vTune, and then look at the results. All right, I will exit here presentation, and I'll open the floor to any questions y'all might have before I go closing out my vTune software. It is available on Beacon. Beacon has. We'll say this: they do not have this, as far as I'm aware, on standard P. But in our case, we have, because it's a smaller deployment, and it's difficult to work out the licensing. We're able to have full vTune for Beacon. And the profile, not just on the mic, but on anything that has no problem. Even your little laptop. Any other questions? All right. There are no more questions. Thank you all for being here. I appreciate the last few days you guys coming to spend some time with me and learn about the Pi. Don't forget, we'll have another actually, are we going to have another presentation on Tuesday, or will it be the next? Spring breaks. There won't be presentations next week. It'll be the week after. Tuesday will be the next presentation. So take off, enjoy our UT spring break. Hopefully it feels springy where you are. And thanks again. And once again, have a wonderful day.